In the previous video, we looked at this integral and found that in the process of doing the partial fraction decomposition, in order to find a and b, we needed to solve this equation. In the previous video, we used the equal coefficients method, but now we're going to look at another method called the convenient values method, which is sometimes quicker for solving these kinds of problems. So what we want to do is notice that this expression is going to be true if we put in the right values of a and b for any value of x. That means if we pick specific values of x, then a and b have to be true for those specific values of x as well. So let's cleverly choose some values of x. If we pick x equals 2, note that then this expression, x minus 2, will equal 0. Sometimes this method is also called the zero method, because you'd like to pick values of x that make something 0. So what happens when x is 2? That means we get 2 minus 8 equals a times 2 minus 2 plus b times 2 plus 1. This gives us negative 6 equaling 0 plus 3b. Notice then that we can very quickly solve for b. b is equal to negative 2, which is the same thing we got before. What would be another convenient value for x? Another convenient value for x would be negative 1, because negative 1 will make this term equal to 0. If we plug negative 1 in for x, we get negative 1 minus 8 equals a times negative 1 minus 2 plus b times negative 1 plus 1. This simplifies to give us negative 9 equals negative 3a plus 0, allowing us to quickly solve that a is equal to 3. Sometimes when we're solving partial fraction decomposition of a rational expression, such as the one below, we will have an improper rational expression. Remember that a proper rational expression is a rational expression where the degree of the numerator is less than or equal to the degree of the denominator. So in the example below, the degree of the top, the numerator, is equal to 5, and the degree of the bottom, the denominator, is equal to 2. Because the degree on top is greater than or equal to the degree on bottom, this is called an improper rational expression. In order to do partial fraction decomposition the way that we've learned it so far, you must have a proper rational expression. Remember that when we did our reasoning to say what possible forms of fractions you could have, we were looking at a quadratic on the bottom, and we were making the assumption the top of the fraction was linear. So before we can actually do a partial fraction decomposition, we're going to have to make this improper rational expression proper. And we're going to do that by long division of polynomials. Now, there's another video that reminds you how to do long division of polynomials if you've forgotten. But what I want to talk about right now is how to determine the form of the partial fraction decomposition without having to actually do the long division. Because sometimes they ask you a question on an exam that says just give the partial fraction decomposition form. And then if we had to do long division, it would take a lot longer. So what I want you to notice is that if we were to do the long division, this x, the fifth term, would be divided by the x squared term, and the first thing we'd be looking at would be an x cubed term. So after we did long division, we would know that we would have some number times x cubed plus some number times x squared plus some number times x plus a constant. That's what we would get when we did the long division. Plus we already know that when we factor this bottom, we get x plus 1 times x minus 2. So we would get e over x plus 1 plus f over x minus 2. So we can look at the original rational expression, and even if it's improper, we can write down the form of the partial fraction decomposition by subtracting the degree of the top from the degree of the bottom. So 5 minus 2 gives us 3, and saying that we might get every term from x cubed on down when we do the long division. And then we add to that the terms we get if we actually do the partial fraction decomposition of the remaining fraction after the long division. Let's talk about repeated linear factors. So far we've looked at partial fraction decompositions of rational expressions where each linear factor only occurred once. What if instead we were looking at something like 3 over x minus 1 squared x plus 2. What would be the form of the partial fraction decomposition for this? Well, first we check the degree of the top is less than or equal to the degree of the bottom. The degree of the top is 0. The degree of the bottom is x cubed if we multiplied all these out. There's an x squared coming from here and an x coming from here. So what can we say about what this form should be? We already know kind of from before that there ought to be, an x minus 1. And we know that there ought to be an x plus 2. But what I want to convince you of is that the only other term we need is the x minus 1 squared. And that we're going to be able to have constants on top of each of these. So if we were to add, first of all, if we were to add these expressions together, do you agree that the common denominator would be x minus 1 squared times x plus 2? If you were to simply multiply all three of these, you would actually get x minus 1 cubed x plus 2, because you'd be multiplying these two expressions. But that wouldn't be the least common multiple. The least common multiple would be x minus 1 squared x plus 2. We would multiply this first fraction by x minus 1 times x plus 2. We would multiply the second fraction by only x minus 2 on the top and bottom. X plus 2 on the top and bottom. And the third fraction we would multiply just by x minus 1 squared on the top and bottom. The second thing I want to convince you of is that we again can't have any other possibilities. If we had x minus 1 cubed, say, we'd have to have a cubed in our final added together fraction. If we had any other things in the bottom, they would change the least common multiple of our expression. They would change the denominator of our added together fraction. Now, the last question is, why is it okay just to have single numbers on top? Well, it makes sense that if we're decomposing a proper rational expression, then each term would be proper. So having just a number over the linear terms makes sense. But what about the x minus 1 squared term? How do we know that this is a b? How do we know it's not something like bx plus c? Or d, I guess, since we already used c. How do we know that that's not going to be linear? Well, if it were linear, it turns out that you could actually simplify it down to rewrite it so that this part of the fraction was actually included over here in the x minus 1 term. So it turns out to be sufficient algebraically to write them in this form. A over x minus 1 plus b over x minus 1 squared plus c over x plus 2. And in fact, in general, we can say if we have a polynomial over x minus a to the n, we can write that out as a over x minus a plus b over x minus a squared plus c over x minus a cubed plus ... plus whatever letter we're on. I don't know, we'll say z over x minus a to the n. So you just write out every possible power underneath, and that allows you to just have numbers on top, which is nice when you're solving for them. And we've kind of been using this implicitly, but let's state explicitly that if you have two linear factors multiplied together, or any number of different linear factors in the bottom, you just add together their partial fraction decompositions. So that's what we did up here, right? We used this new rule to write out x minus 1 and x minus 1 squared, and then we added that to what we got for the x plus 2 term. Irreducible quadratic factors. Sometimes we have an irreducible quadratic factor in the bottom of our partial fraction decomposition. So if we had something like x squared plus 1, that's irreducible, times x minus 2, 3 over x squared plus 1 times x minus 2, then we know what to do with the x minus 2. We just write that as a over x minus 2. But what do we do with the x squared plus 1? Well, it's irreducible. That means we can't factor it anymore. So the bottom of this fraction is going to have to be x squared plus 1. We know that because we're starting with a proper fraction, each of these fractions in the partial fraction decomposition will also be proper. So we know the worst case scenario is this is bx plus c. But since we don't have any linear terms that go with this one, like we did before when we had repeated linear factors, we can't do any better than bx plus c. So when we have a irreducible quadratic factor, we have to put a linear factor. top. So another example, if we looked at something like 3 over x minus 2 cubed, x squared plus 1 squared, this is repeated irreducible quadratics. We know what to do with the x minus 2 cubed. We get a over x minus 2 plus b over x minus 2 squared plus c over x minus 2 cubed plus, now with the irreducible quadratics, we're still going to repeat that so that we have one for each power. But now on top, we have to put linear expressions, so dx plus e and fx plus g. So in general, we can say that for a irreducible quadratic, ax squared plus bx plus c to the nth power on the bottom, we are going to write it out like, let's say a1x plus b1 over ax squared plus bx plus c to the first plus a2x plus b2 over ax squared plus bx plus c squared plus a3x plus b3 over ax squared plus bx plus c cubed plus, let's say dot dot dot, plus anx plus bn over ax squared plus bx plus c to the n. So you just do the same thing you did with repeated linear factors. You repeat the quadratic factors as many times as you have that power, but now every time you have to have a linear equation on top. So in general, you just put all this stuff together, and you can say that, if you know how to do each factor to their power, then you get, then you just add up all of those partial fraction decompositions. So in general, we know how to do linear factors raised to a power, and you get whatever that power is, you get that many terms, and then you fill in the same linear factor inside, and we put a number on top. For irreducible quadratic factors, whatever the power is, you get that many terms, and you put the irreducible quadratic inside, and then on those you put linear equations on top. And if you have multiple terms in the bottom, you just write out the decomposition for every factor and add them all together.